So, in video number 3, we're going to talk about first the membranes that make up the alveoli, which will help contribute to our negative ventilation. So first, we have surfactant. Surfactant is everything in this space. And second, we have the alveolar. The outermost layer of all of this. Here we have an alveolar cell, or a sac, excuse me. As you notice, one is bigger than the other, and that is for pressure reasons. We also have here a pleural space, and I'll show that to you on the lung that I drew. This is the pleural space, and this is where there'd be ribs here, and this is what is helping to create that negative pressure inside of the lungs. So the job of this surfactant here is to maintain surface pressure. When we lack surfactant, our alveoli will collapse. And they collapse because this maintains that surface pressure. If there's none of this, then there's no surface pressure and everything kind of falls inward and they collapse. That's the same for all of this. Every alveoli, has surfactant. This pleural space that I had just mentioned here has a negative 5 millimeters of mercury pressure in it, and so it is negative, and because of that, it holds it open, as in this. If we were looking at it, this would be the left lung. But the total atmospheric pressure is 760 millimeters of mercury, and then that partial pressure of oxygen is 21%, and so it's 160 millimeters of mercury there. When we get a pneumothorax, there is a breach in that pleural space which rushes air out, which collapses this lung here because it is now a positive pressure environment. So because all of this air has left, there's no more negative pressure holding this lung outward and holding it against that pleural space, which is mostly full of water and other fluids. So the partial pressure of oxygen that enters into through your mouth here would be 160 millimeters of mercury. As it travels down and through and into the alveoli, these represent little oxygen molecules, and we find that the PaO2, which is the partial pressure in the alveoli, is 102 millimeters of mercury. Mercury will be. When we talk about CO2, it's a little bit different. So the PA of CO2 here in the alveoli, and this is just a simplified alveoli, is about 40. in the blood, we have bicarbonate that binds with hydrogen protons. It creates water and CO2. That CO2 dissolves slightly in the blood, and so it's currently at 45 millimeters of mercury, but because of that slight dissolving, when it moves into this, we find the PaCO2 is 40 millimeters of mercury, so it has lost a small amount of pressure, and because of that, you need less pressure for the CO2 to actively be working. The final piece that I want to talk about is the oxygen hemoglobin dissociation curve and some of the factors that can affect it. So on this curve, this middle black line we'll consider north. So the more percentage of hemoglobin that you have, the more percentage of oxygen attached to hemoglobin, the higher your oxygen saturation rate. I've drawn this here. If we go below 75% of the hemoglobin of oxygen being attached to hemoglobin, then we'll be at about 40% of oxygen in our blood. And if we reach this level here, we will lose it very quickly. As you can kind of see, the graph turns down on all three of these. But it's kind of even out here in the middle, and as we get up, it's sort of an exponential curve in a way. But we do have these shifts, and the first is the left shift, and then this blue line is the right shift. When we are in the left shift here, we are in the R state, because it means that more oxygen is bound to the left state, the right shift means that there's less oxygenated hemoglobin. Some factors that can affect these left or right shift, one major one is CO2. Concentration of CO2 in our blood will be majorly right shifted, and that is because it holds the oxygen, or it holds the hemoglobin in their T states, which will prevent them from binding oxygen. Temperature can affect it. If you have a really high temperature, then you could have a left shift as well, and you could be having a hard time breathing. And then the same thing with exercise. This PPDGT is something found in the placenta of mothers, and it usually presses tissue on a fairly regular curve. Curve. But there's lots of other factors that can affect whether you shift right or left. And each one of those is very simple. If you shift to the right, and you're in the T state, then you have less oxygen. You can see here, if you're down here, then your percentage is dropping, and your oxygen saturation will drop in conjunction with that. But if you are higher, you shift it to the left, then you have more. There's more affinity for it. But that is the dissociation curve.